Hello everyone, this is Dheeraj, pursuing my BTech second year in ECE from VVIT. My topic is Fermi energy level. The Fermi level is the highest energy state that an electron can occupy in a material at absolute zero temperature. So, in extrinsic semiconductors, which are classified into N-type and P-type, in N-type semiconductor, the Fermi energy level is as follows. The electron concentration N or donor ion concentration Nd in n-type semiconductors is given by Nd equals Nc into e power minus Ec minus Ef by Kt. So by deriving this, we get Ef equals Ec minus Kt log Nc by Nd, where small n equal to electron concentration and Nd equals donor ion concentration and Ec equals to minimum energy level of conduction band. In p-type semiconductors, hole concentration P or acceptor ion concentration Na is given by Na equals Nv into e power minus Ef minus Ev by Kt. So we got these expressions from Fermi-Dirac distribution, as we all know. So by deriving this, we get Fermi energy level in p-type semiconductor Ef equals Ev plus Kt log Nv by Na. Here P equals hole concentration, Na equals acceptor ion concentration, and Ev equals maximum energy level of valence band. And in both the expressions, K equals Boltzmann constant, T equal to temperature in degree Kelvin, and Ef equals Fermi energy level, as we all know. Uh, NC and NV are constants having the dimensions of concentration NC and NV as follows, where NC equals 2 into 2 pi mn kt by h square whole power 3 by 2 into q power 3 by 2, and NV equals 2 into 2 pi mp kt by h square whole power 3 by 2 into q power 3 by 2, where mn and mp are effective masses of electron and hole, and q equal to charge of an electron and h equal to Planck's constant. So now let us discuss about Fermi energy level in an intrinsic semiconductor. In an intrinsic semiconductor, electron concentration is equal to hole concentration, which is equal to Ni, that is intrinsic concentration. So we know that electron concentration is Nc into e power minus Ec minus Ef by Kt equals Nv into e power minus Ef minus Ev by Kt, which is equal to intrinsic concentration. And we get the ratio of Nc and Nv, that is, we get the ratio of the constants in order to get the Fermi energy level of an intrinsic semiconductor. So there are two cases. If Mn equals to Np, that is effective masses of hole and electron are equal, then Nc equal to Nv, as Nc and Mn are directly proportional and Mp and Nv are directly proportional. So by deriving this, we get Ef equal to Ec plus Ev by 2. So this is the energy band diagram where Ef equal to Ec plus Ev by 2. That means it lies exactly in between conduction band and valence band. So case 2. If Mn is not equal to Np, then we get Ef equal to Ec plus Ev by 2 minus Kt by 2 log Nc by Nv. That is, we get the Fermi energy level below the, we get the Fermi energy, we do not get the Fermi energy level exactly in between, but we get it below the half of the level from, we get maybe, it might be here. So now let us discuss about variation of Fermi energy level in extrinsic semiconductor with concentrations. In n-type semiconductor, we know that electron concentration equal to Nc into e power e minus Ec minus Ef by Kt, and we get the Fermi energy level in n-type semiconductor as this. So we will consider three cases in the variation. The first case is Nd less than ND is less than NC. So if ND is less than NC, then the ratio NC by ND will be greater than 1. That means the logarithm value of NC by ND will be positive as NC by ND is greater than 1. So if we substitute this positive value in the Fermi energy level of n-type semiconductor, we get EF equal to EC minus some positive value. So as EF equal to EC minus some positive value, we get EF less than EC. As EF is less than EC, the Fermi energy level lies just below the conduction band. Case 2, ND equals NC. So if ND equals NC, the ratio NC by ND becomes 1. So logarithm of any value, logarithm of 1 equals to 0. So EF equals to EC. As we substitute a logarithm value in this equation, Fermi energy level equation, we get EF equals to EC. So the Fermi energy level is equal to the conduction band level, minimum energy level of conduction band. So it lies here as shown. If ND is greater than NC, which is third case, NC by ND will be less than 1. So logarithm of NC by ND, that means which is less than 1, might equals to negative value. So if we substitute this negative value, logarithm of NC by ND equals to negative value in the Fermi energy level of n-type semiconductor, we get EF equal to EC minus some negative value. So negative of negative will become positive and EF equal to EC plus some positive value. So EF is greater than EC. So it might EF might go into the conduction band. Fermi energy level of n-type semiconductor might go into the conduction band. In the case ND greater than NC. So in n-type semiconductor, as we all discussed, as we discussed these three cases, we conclude that in an n-type semiconductor with increase in doping Fermi energy level moves towards conduction band. And for heavily doped cases, it may even enter into conduction band. So this is the case where the Fermi energy, this is the case where Fermi energy level it may even enter into conduction band. P-type semiconductor. Variation of Fermi energy level in P-type semiconductor. So we know the we know that P-type concentration equal to Na equal to Nv into e power minus Ef minus Ev by kT, and Ef equal to Fermi energy level in a P-type semiconductor equal to Ev plus kT log Nv by Na. Here we will consider three cases again, same as previous, which is Nv greater than Na and Nv equals Na and Nv less than Na. So Nv by so the first case, which is Nv greater than Na. So we consider the ratio Nv by Na, which is greater than or equal to 1, and log of Nv by Na will be positive. So EF equal to EV plus KT log NV by NA. EF equal to EV plus some positive value. So EF will be greater than EV. And the Fermi energy level lies above the valence band, maximum energy level of the valence band. So the second case, NV equal to NA. NV by NA equal to 1, as they both are equal. So log 1 equal to 0 and EF equal to EV. So Fermi energy level equal to maximum energy level of valence band. So the third case, NV less than NA. If NV by NA is less than 1, then logarithm of NV by NA will become negative and EF equal to EV plus KT into some negative value. So EF equal to EV minus EF plus some negative value. So EF will become less than EV. As EF is less than EV, EF will go into the valence band. So According to these three cases, for p-type semiconductors with increase in doping concentration, Fermi energy level will move towards the valence band. For heavily doped cases, it may even enter into valence band. So the heavily doped case is the third case. So this is all. Thank you. Thank you very much.